list, right? Here's my list. And it goes on forever. If I wanted to print out all the values in this list, there's a fairly natural way to do it. What's the fairly natural way to do it?
Left to right.
Left to right. Start here and just go there, right? I might do it in reverse, but if someone said print this list in reverse, you automatically know what that means. And there's not any question. It's like, okay, these are very obvious ways to do things. All right, now, I have a tree. This one's not full or anything. Just A, C, D, F, G, H. Now I say, print out all of the nodes in this tree. What's the obvious way to do it?
Reverse.
Well, that's how we're going to end up doing it, but yeah.
I would say that you would go down the farthest left one until you get to the bottom and then print the value for that and then just go up and keep on going left, right?
That's not a bad way to do it, but I don't know if everyone else would have thought that's the natural way to do it. Different people would have had different ideas because there's no real obvious, this is just the way you do it. Just like with this list, I don't even have to really explain the concept. But the very first time I showed you a list and said, now I want to go through all the elements, you guys all immediately thought, oh, he's just going to do that. Right? When I do that for the tree, you're thinking, oh, just go all the way down here and do all that. Okay, great. Someone else might have said this, then both of these, then all of these, then this. Someone else might have said, we'll do them in order. A, B, C, D, E, F, G, H. Yeah. So the point is, there's no obvious way. There's no just, when I say obvious, I mean natural. There's no just natural way of doing it. So we still want to go through trees. And it's called traversing a tree. And there are many different traversals. I can think of 5 right now, and there's probably fancier ones, but 5 common ones. We're going to talk today about 3 of them, and then next week we'll cover the other 2. The general form of recursive traversal is something like this. If T, my tree, is not empty, then I'm going to display the data in the root of T, and this is for a binary tree. Okay. I'm going to display the data in the root, and then I'm going to traverse T's left tree, then traverse T's right tree. Since T's left and right subtrees are proper trees, then I can call the same thing, traverse, which is the same method. I can call it recursively and just do the next level down. This is not complete because with recursion, remember I need a base case, and I don't have that put in. Well, the T's not empty. Okay, yeah, that counts. So if I applied this mechanism to my tree over here, I would print out A, then I would go to the left subtree, I'd print out B, then I'd go to the left subtree, I'd print out D, then I'd go to the left subtree, I'd print out E, then I'd go to the left subtree, and that's empty. So I would do nothing. I'd come back up here and print out E's right subtree, which is empty. So I would come back up here, and I would say, all right, D, you printed yourself, you printed your left subtree, now print your right subtree. I'd print F, and then I'd go to this subtree, and then this subtree, the empty ones. I'd go back up, now to B, now to G, and so on. So this would end up with A, B, D, E, F, G, C, H. So that's just the general idea. Now, we have, what I mentioned, we'll talk about 3 different variants of this kind of traversal today. But the key point you're supposed to learn from this is and understand the recursive structure of this kind of a traversal. I start with the root, but I don't know it's the root. I get passed in a tree, and I look at the root, I display the root, or do something with it, and then I'm going to recursively call myself on the left subtree and then the right subtree. And on that recursive call, I'm going to do the same thing. The recursive call doesn't know that it was called from the parent. The recursive call just says, oh, hey, I'm in my root, print the root, then left and right, and so on. This idea, where I display, then I do left, and then I do right, this technically has a name called pre-order traversal. The reason this is called pre-order is I'm going to visit the root before I visit the children. So pre-visit and then visit the children. You'll notice that this structure is exactly the same as this. It's just that I filled it out with more code. So this is called pre-order. I send in the tree, bin tree. If the bin tree is not empty, I visit the root. And after visiting the root, I do pre-order of left, which is a recursive call back into this. And then when that recursive call returns, which is the whole subtree gets done pre-order wise, when that comes back, then I do pre-order on the right subtree. So this here helps to trace through that. Just this side. These other two are going to come in a second. So this one is a pre-order traversal of this tree. So remember with pre-order traversal, I visit the root, then left, then right. So can you guys see the blue numbers? So the blue numbers are the order that we print values out in the pre-order traversal. So I start with the root, 60. Now I'm going to do left and right. So then I go to the left, and on the left side, I visit the root, and I print 20. And now what I have pending still, up here, I still have a pending to go over to the right side and do that. But I'm down one level of recursion. I'm going to go down another level of recursion when I call print left on this root. When I call print or pre-order on the left. So when I call pre-order on the left, I print the root of 10. So that's the third element is printed. Now I'm going to call pre-order traversal on 10's left child. So I call on this, which is an empty tree. And so remember, if the tree is not empty, do this. Otherwise, it just returns. So it returns back up, and once it returns to here, I visited the root, and that was my 10. I did pre-order of the left, and that ended up being empty, so it didn't do anything. I still have to do pre-order on the right. So I do pre-order on 10's right, which is also empty, doesn't do anything. So now, at this level, at the level of node at 10, I visited, I did the left, I did the right, I'm done. I pop back up to 20. And at this node, what have I done so far? I've visited and I've done the left, but I haven't done the right yet. So now I go and I do the right. So I did this, now I'm doing this. So it's recursive call in there. And I print the 40, then I do the left, which prints the 50 or the 30. Then I try and do this, and then I back up and do this. So 1, 2, 3, 4, 5, and then empty, empty, 6, empty, empty, back up, and then 7. Okay, so that's pre-order. Make sense?
I got kind of a question. It's like, so how does it know, like, okay, so you called that function like on 10, and it had 0, nothing, nothing. How does it know to go back up? I mean, I can understand recursion is going down and then coming back up, but how does it know that it hasn't already printed 20 or 40 or anything like that? Like, that's what I don't
Right,
understand.
that is, I thought I had one in here. Nope, must be on the next chapter. That's the way recursion works, is it remembers its state. When you call recursion down one more level, you kind of take a snapshot of where you were at that level. So when you return, when you come back up, your statement pointer is waiting now to go to the next statement at that level of recursion.
That makes sense, okay.
Okay, we're all good with pre-order? And notice the order that things got printed out. 60, 20, 10, 40, 30, 50, 70. That's not really meaning anything. Is this a binary search tree?
No.
Wait, yes.
Wait.
Yeah, it is.
Yeah.
Issue of binary
Mhm.
searching files.
Well, I mean, we can rule out, is it a binary tree or not?
Yes.
Great, first part done. Now the search tree part means that everything on the left is less than the node, and the node is less than everything on the right. Are there any nodes in this tree that violate that? No. That makes it a binary search tree. So it's a BST. And this in order or pre-order traversal of the BST gives us these values in almost randomly appearing order. It's not random, it's the same way every time, but not that much. Doesn't make much sense. All right, in order traversal. in-order traversal is very similar. But what we're going to do is visit the left, visit the node, visit the right. So the only difference between pre-order and in-order is we swap these two lines. Right? So I'm going to visit the left, then I'm going to print myself, then I'm going to visit my right. Make sense? So let's see what happens when we do that. This is my in-order route. All right, I started the route. What is the first thing I do?
Visit the left.
I go to the left. I recursively call in-order traversal on the left. So what's the first thing I do? I go to the left again, and the first thing I do, I go to the left of empty, then I come back, and then what do I do? Print myself. Then I go to right, empty, come back. Now I'm done. I go up here, what do? Print the node, then I come down to the right, and here I go left first, then I print left, then I come up, then I print in the middle, then I print, then I go down to print right. I come back up here, I finish the left tree, I print myself, then I go to the right, and I print the right. Now, does that sequence look familiar?
Yeah.
That's an in-order traversal, which conveniently puts the nodes in order. If you have a binary search tree, an in-order traversal prints everything out in order. It's a very handy property. So imagine I was storing a bunch of data in a binary search tree and I wanted to print everything out in order. What do you think I would do? In-order traversal will give me everything in order. And what's that?
Seems kind of self-explanatory that way.
Yep. So again, though, I want to point out the difference between my pre-order, visit left right, and in order is left visit right. So there's one more. Can you guess what it is?
Post order.
Post order. And what do you think post order does?
That's right.
Left right visit. Okay, so this is very similar to the other one. It's do left, then do right, then visit. Okay, this is the children first strategy. So I start here. I'm going to print that guy, post order. This guy is going to print that guy, post order. Then this is going to print its empties. It's going to print this. Come back up here. I don't print yet. I don't, because I only did one of my children. I do my other child. And this one comes down here. Then it prints 30. Then it prints 50. Then I print 40. Then I print 20. Then this guy up here 60. It's printed all its left. Has not done its right yet. So it calls and prints the right. So I print 70. That comes back up, and then I print 60. So I get things added. So, in order, it makes sense when we might want to use that, right? When we want to print things out in order. Any idea when we might want to use post order?
Destructor.
Exactly. When we want to destruct this thing. If I've got all these nodes in here that are dynamically allocated, when I want to free them up so I don't leak memory, the best way to do this is a post order traversal. Because I don't want to delete this node until I've deleted all my children. Right? Sounds a little bad, but so we delete the children first and then we delete ourselves.
So effectively the post order traversal is removing the bottom layer of leaves every single time.
Right.
In the idea of the leaf.
Right. But it actually, you're right, but it goes to the very bottom first and then kind of unwraps all the way
Yeah,
coming
it goes
up.
to the bottom, then does the next
Right.
level up, then the next level up. So
But not quite as in, I'm going to do all these, then I'm going to do all these and all these. It looks that way now
Yeah,
because if this was fuller, if this came down, if there was an 80 and a 90, I wouldn't delete 30, 50, and 90 first. I would only be doing this half of the tree.
That's the recursive bottom
Yeah.
starting to the left.
Right.
That's all the leaves starting to the left.
Right. So if I had an 80 and a 90 here, everything would be the same, 1, 2, 3, 4, 5, and then I wouldn't do 6 first. I would do empty 80, but I wouldn't do 80 first, I would do empty 90. I'd end up doing 90. Then I would come up to 80 and do that. Then I would hit 70, then 60. Does that clarify for you?
yes, thank you.
Okay, so That's our post order. So this is one of the reasons why I thought trees were so great, is because by this time I already knew recursion and I thought recursion was the coolest thing ever. And now here was stuff that used recursion. And look, I can traverse the tree 3 different ways just by rearranging the order of these 3 statements, which I thought was pretty nice. And then I